Hi, and welcome to today's session on error cost and meaningful human oversight, which means how humans in the machine learning loop can actually help in machine learning applications. So first of all, a prediction is not a decision. So what we've looked at so far with probabilistic predictions, with calibration, entropy measures, and also conformal predictions, we just saw methods how uncertainty can be quantified. However, the decision rule, so depending on your machine learning application, there must be some decision rule that determines what happens next. And today's question is, who sets that rule and who bears the cost when it's wrong? So here, let's look at this example. Wait, just let me put on my laser pointer. If we get a probability of 0.72, we maybe have like 3 different options. Either we do nothing, we ask a human, or we intervene. The big question here is, what is then basically chosen? What is the decision that is done? Because the probability itself, so the 0.72, is just the number that the model predicts. And this decision will always be determined by whatever process is behind here. And also the same score can lead to very different actions because a score itself does not contain, for example, the costs, the rights, the rules, values, and so on that are needed for a decision. So here we can look, for example, at the predicted probability of 10% that one email is spam. What can be done would be, for example, to move this email to spam. However, if we are not in this, I'd say, kind of simple example where errors or mistakes are not too severe because, I mean, the email is just moved to a different folder, it's not deleted, and there's nothing else done directly. But instead we are in a more serious example, for example, in diagnostics of some diseases. A 10% predicted probability could, for example, lead to a follow-up test. A 10% probability of welfare fraud might lead that to a new review and the person is not sanctioned directly because if we mistakenly sanction someone, the consequences would be much more severe. And basically what I try to tell you with this example is that even though the predicted probability is 10% for all of those examples, it does not directly lead to a plausible action. Because every threshold exchanges one kind of error for another. So if we have, for example, a very high threshold, so the values need to be very, very high for us to actually have an action, there might be more missed cases. However, if the threshold is too low, we might have too many false alarms. And talking about false alarms, I want to present you some rare events next. So imagine we have, for example, some facial recognition software that checks at the train station all the visitors and wants to find criminals. If we have 180,000 people passing through that train station every day, and we assume that, for example, there are actually 10 people that are sought by the system passing through the train station, and we have a 90% sensitivity for this system. So 90% sensitivity means that out of all the true cases that we're trying to find, there will actually be 9 of them recognized, so there will be 9 true alarms. And if we, for example, have 0.1% of false positive rates, so out of basically all people that are checked, so all the 180,000 people, 0.1% will have a false alarm, which leads for for such numbers to 180 false alarms. So here it's visualized. All the dots are alarms, the gray dots are false alarms, and the green dots are true alarms. So you can see out of all those alarms that we have in one day, out of 180 or about 190 alarms, only 9 of them will be true alarms, so true criminals that are sought by the system, which means that only about 1 in 21 alerts would actually identify a sought person. And I want to present you this example because it directly shows that even though we might have a quite well-performing system, if we say 90% sensitivity and 0.1% false positive rates qualify as a good system, we still have the problem of what happens now with those results. Because obviously, if only 1 in 21 alerts actually supports or shows a real criminal, I wouldn't say that all of those 190 people, or about 190 people, should really be, I don't know, directly taken to the police and questioned and kept all day and so on. But there really needs to be like another process how to act on those alarms. And yeah, this example is just to sensitize you about how to act on the results that a machine learning can give you. A threshold is a policy choice. So basically the questions here are: what action does crossing the threshold trigger? How harmful and reversible is each error? Who benefits and who bears the burden? What legal or evidentiary standards apply? And is there a safer intermediate action? So again, all that shows you how to think about how to set certain thresholds, or what to think about when you actually then apply your machine learning model in practice somewhere, and really think about, okay, it basically directly relates also to fairness, like who receives the benefits, who bears the burden. It's really a question, are people treated equally, or where are the differences? What happens if the threshold is basically happens? And this also directly leads us to the human-in-the-loop machine learning, which is when a human actively participates in the operation, supervision, or the decision-making of an automated system. This can all lead to improved accuracy, safety, accountability, or ethical decision-making. So here in this graphic, we can see that, for example, when we have an input to an AI model, humans can provide the annotations, for example, so they could provide the labels. Then the AI predicts something. We can have, for example, check the confidence levels, just as we talked before about many different methods how to quantify the confidence. And if we have low confidence, we can again give that to maybe different humans, or depending on the setting. Basically people that can check what happens next. And ideally you also have a loop that whatever the human does then can be annotated again and used to better train the models. And ideally, if the confidence is high, you can have this automated pipeline directly from the AI model to the outcome. Which is a nice principle, of course, but again, it has caveats. Namely, we can have over and under reliance. So people may follow incorrect model advice or ignore useful recommendations. We can have decision variability because, for example, if the expertise, the incentives, the workload, or the risk preferences of different people vary, it also affects how those predictions are translated into actions. Also, the predictions shape the judgment, so model outputs can anchor attention and influence which factors humans consider. And here, if we look at this small graphic here, we have an AI robot. I understand you're the human in the loop, and it just floods the human with tons of AI approval requests. For example, those 190 examples of people that are detected by our automatic train station security program. Other caveats of human in the loop are selective outcomes. So human interventions determine which outcomes are observed, and we basically create biased data for this evaluation and retraining, just as I showed you in the graphic before. We also have feedback loops that the decisions change the environment and future data, reinforcing earlier choices in the end. Also, there is unclear accountability because the responsibility, it becomes difficult to assign when outcomes result from those joint human model decisions. So was it the model that gave you the a wrong prediction and that led for the human to decide wrongly, or did the human make the mistake, or where is the accountability coming from? So in general, a human in the loop does not automatically make a machine learning system safer, fairer, or more accurate, but it can. And with that, we want to thank the DFG and our copyright. Thank you, everyone.